shape, like it's common, are they derived from this, the magnitude? Like, is that a component that is in each and every single, not every single, but like it's familiar in every single function, like for a sphere?
So as we're going to see in this class, right now the only type of functions that you've ever studied are what we call scalar functions. F of x equals what? Like functions you've studied, right? F of x equals x sine x. That's called a scalar function. It takes in a number, spits out a number, doesn't it? Okay, we're going to study other scalar functions in here that you have not studied before. Functions of more than one variable, where you take two numbers in and you spit a third number out. Okay? X squared plus y squared. That's an example of both of these are examples of scalar functions. You're taking numbers in and you're getting numbers out. We'll also study functions of three variables. Give me three numbers. I'm going to spit you out a fourth number. So, I don't know, x plus y plus z. All three of these are called scalar functions. So you're asking me a question about functions. The reason I'm answering like this is because I can't answer your question because we have scalar functions and then we have vector functions, which nobody in here I don't think has worked with yet, where you take in a vector and you spit out a vector. That's a vector function. Vector input, vector output, right? So when you're asking that, that's too abstract of an idea because I need to know exactly what type of function you're talking about. Scalar, vector, make sense?
Yes, sir.
Okay, so maybe down the road I can answer that a little bit better if you want to talk about one type. Yeah? All right, so this is an opportunity for us to practice. I'm going to skip the first one here. I'm going to go to example 4 because this is three-dimensional. If we can do three-dimensional, 2 should be pretty easy. Yes?
So the process of taking the magnitude of a vector, get output to scalar?
That's right. You take the magnitude of a vector, you can get a number, which is the length, right? So that vector right here has a length. All vectors have a length and a direction. Right now, if someone gives us the components, right, the angle bracket, if someone gives us those numbers, I can tell you how long it is. We still don't know how to find the direction yet, do we? But I can at least get you the length. Yeah? So let's do it on this one.
Use trig to find our angle.
If you're in R2, you can. But in R3, it's not as simple.
Yeah, R3 would get harder. But
It would get harder because, you know, where are you relating it to? And we're going to address it. We got a great thing coming, all right?
oh boy.
We have a great thing coming. So, all right, here we go. We've got two vectors, v and u, all right? I've given you the components of the vectors, right? The components. And the first thing I'm asking you to do is take v and subtract u. So let's just make sure we can do that. So this will be equal to a vector, right? If I subtract two vectors, I should get a vector? All right, so I'm going to have three components here. My first component of that vector is what? What is the actual operation I'm going to do? If I'm subtracting, right?
2 minus u, would be 2 minus negative 5. So
2 minus negative 5. We're going to take the first component here. We're going to subtract negative 5. So 2 minus negative 5. And then the second component would be 3 take away 7. And then last one, negative 5, take away negative 2. Am I pushing too much to say that's pretty simple, like just arithmetic? It's just you got to make sure you get the order correct, right?
yeah.
There's nothing crazy about this. Let me put the answer above it. It'll be 7, negative 4, what do we got, negative 3? Good? That's what happens when you subtract those two vectors. Now, without doing any work, what do you think happens if I do it the other way? It'll just change the signs. How could you convince yourself of that without doing any arithmetic? How could you try and convince me of that?
Just goes the opposite direction.
Why though? Why does it go opposite direction?
Because the scalar is opposite. Negative, excuse me.
Yes, I think I want to say yes.
multiplying.
Here's what I want you, here's kind of what, you're saying the right thing, but here's the way I want you to see it. U take away V is the same as doing the opposite of V take away U, right? Because if you scale this here and here, this one becomes negative, that one becomes positive, and then that's this, isn't it? So it's this vector, but pointed in the opposite direction. So I just take that vector, point it in the opposite direction by multiplying it by -1. So the answer to this one is -7. That's what you're saying, right? Okay. All right, how about finding this vector, 4v minus 3u? So what is 4 times v? Scalar multiplication, right? I'm taking the vector v and I'm scaling it by 4, which should make it longer, shorter, flip it, what? 4 times as long. And I'm subtracting 3 times u, so I'm taking u and I'm making it 3 times as long, but then I'm taking it away. So, yes?
Is there a PEMDAS for scale vectors and stuff like that?
A PEMDAS? Well,
Order of operations.
order of operations, we'll have some properties here that you'll see that it's the same PEMDAS, I guess, if you want to call that from before. But see, the problem is our operations are different, right? With PEMDAS, you only had, addition, subtraction, multiplication, division, exponents, parentheses, right? Here, we have 3 types of multiplication, right? So how does that work? What if you had 2 of the multiplications together? Which one do you do first,
Yeah,
right?
exactly that question.
Well, stay tuned. It's coming. All right, so this one, let's write down what is 4v? What is 4 times v minus 3 times u? So let's try and do this kind of mentally here. If I ask you for 4v, you're going to take the vector v and do what with it?
We multiply 4 times.
Multiply each component by 4.
You get 8, 8, 12, negative 20.
8. You said 8, 8.
8, 12. I said 8, 12.
Oh, you did? I heard 8, 8.
You said
Okay.
8, 8, 12, negative 20. You said 8 twice.
Oh, yeah, well, I
It's
went
on
to
video.
say- I went
We're going to
say
go back and
stop.
audit the
Say it
video.
again. Don't worry.
All right, 8, 12,
I'm gonna put a comment.
8, 12, negative 20. And then the other one, 3 times that's a negative 15, 21, negative 6. And now you're going to subtract. So we'll just do 8, and then we will take away negative 15, right? So 8 plus 15.
Yeah.
And this is a vector. 8 plus 15. 12, take away 21. And then negative 20, add 6.
Yeah, I knew 20.
Sorry, this is like so sloppy. I'm trying to get this all on the camera, Like if I could just go around the room. What would y'all rather have? Would y'all rather have it on video, or would you rather me be able to just go around the room? I never asked you. Do y'all care? You like around the room more?
I think it's cool.
Do y'all care? Maybe I'll send out a vote. Y'all can vote online anonymously.
I think like if you think it's like super important, I think we should try to get it on camera. But if it's like some ridiculously long problem, I think it would just be better more efficient to go around.
Yeah, these are just little easy, to me these are just easy little computations, so I'm not really,
Yeah.
all right. What do we have? Our vector is 23,
9, 14, right?
negative 9, 14. Do we all agree?
Check.
Everyone agree? Yeah. All right, part D, last part. We want the magnitude of the vector we just found. Oh, it's negative 14?
It should be, yeah. Negative.
Yeah, it is negative 14.
Yeah, negative 14.
There we go. Okay, so part D, we want the magnitude. And to find the magnitude, I'm going to use the formula, right? Which is no longer on this page, but I can bring it. I won't bring it up, but so for this, what I'm going to do is take the square root of. I'm going to take each component and square them and add them together, all 3 components. This is going to be a big number. 23 minus 9 minus 14 equals ... I won't do anymore. I'll just leave it. Okay? That would be the magnitude. Whatever that number is, right, would be the magnitude. And if it's not a perfect square, then you can just leave it under the root, right? Like let's say you get root 28. It's not going to be root 28, but let's say in an answer you get root 28. You can just leave it as root 28. Okay, you don't have to go that additional step where you say, oh, that's 4 times 7, and pull out a 2 and say 2 root 7. That step is not necessary for me. It's the same number, okay? It's best to leave your answer in the exact form, like under a root, than to get a decimal. It's better just leave it in the exact form.
It isn't that.
All right, we're moving on.
Just do it all.
Hey, shh. All right, let's move on. All right, any vector with the length of 1 is called a unit vector. So if you're looking at vectors, any vector that has a length of 1 is called a unit vector. So if I imagine, take a blue vector, okay? Doesn't matter where that blue vector is. We're looking two-dimensional. Do you agree that no matter what I do, no matter where I pick a vector, other than the 0 vector, that no matter what vector I ever pick that's blue, there's always going to be a red one pointed in the same direction that has a length of 1.
Yeah.
Like I should always be able to find a vector that's pointed in the same direction as the blue one, but that has a length of 1. Even if I make the blue vector shorter, right? Even if that blue vector is really short, there's still a red vector that points in the same direction that has a length of 1. Yeah, right? So can we find it? Like if someone gives us a vector, can we find a vector that points in the same direction but has a length of 1? Right? That seems like a reasonable question. Can we find, given the blue vector, can we find the red vector? And the answer is yes. All we have to do is scale it, right? Imagine you have a blue vector, right? Let's say that blue vector has a length of 10. What would you need to do to make it have a length of 1? Divide by 10, right? Scale by a tenth, right? You'd want to scale it by a tenth. So what we're going to do here, if we're given any vector, right, given any vector u, and we want to find a vector that points in the same direction but is a unit vector, what we will do is we will take that u vector and we will scale it. See, this right here is a c. It's a number. And do you see what it is? 1 over its own length.
Yeah.
See, you're multiplying the vector u, you're scaling it by 1 over its length. So like you just said, if the vector u was 10 units long, you would multiply it by 1/10 to make it shrink down to be 1, right? That's what this is. So that's why that's one little aspect of why it's nice to be able to find the length of a vector, is because then you can find a unit vector in the same direction. Now, are you wondering why you'd ever want a unit vector? Maybe, I don't know. Maybe we're too far, I don't want to get too far ahead of ourselves, but later on, when we're dealing with vectors, vector functions, and we're dealing with things like vector fields, like electromagnetic fields, we can imagine an object that has, or gravity. Gravity is a little easier for us to understand. If you have an object, you have gravity pulling, right? You want to visualize what that pull is, that's a vector. But a lot of times what we want is just simply the direction. And so we'll use the unit vector instead of the entire vector. And then we can do something with that and then figure out the direction of our particle and then put those two vectors together somehow and get some result. So the unit vector is useful later. Yes?
Is there any special notation for the unit vector?
No. Yes?
Does the 0 vector ever come into play, or is that just?
The 0 vector, you can look at the 0 vector as like the number 0 in our number system, right? Like it comes into play because there's an important properties. Like if you add the opposite, like take a number, add its opposite, right? You get what? 0, right? So with vectors, we always need that it's actually got a technical name. I know, who are my math majors? I saw a couple of people who said math, right? So 2 or 3. So every field, a field is a mathematical structure. Every field has to have an additive identity, which is something you can add to the things that doesn't change them. And so the 0 vector is our additive identity. It has to be there. So just zeros come up, right, in our normal calculus. Like, have you ever added 0 somewhere in an equation? Like seen a hidden 0? I don't know if in the... Like, did you ever like introduce something, like add it and subtract it at the same time? that sort of thing. Like that's an important use of zero, right? The zero vector has that same ability. You can look at the zero vector as any vector minus itself, or you know what I mean? So it does, yeah, it has lots of roles. But we have to have it there or else you don't have a field. All right, we're going. Let's do an example. So this one right here, I'm going to give you a vector. We want the vector that is pointing in the same direction as this vector v. All right, find a unit vector which points in the same direction as that vector v. So what should I do first?
Find magnitude?
Find the magnitude, right? So let's do that over here. First thing I'm going to do is let's find the magnitude of v, which should be the square root of the sum. Listen to the way I say that. I'm going to take the square root of the sum of the squares of the components, right? So I'm going to do 2 squared plus 3 squared plus negative 5 squared. This should be square root of 4 plus 9 plus 25, which is the square root of 38? 38. And I'm just going to leave that as that, square root of 38. Now that's not my answer, right? That's just how long that vector is, square root of 38, right? That's how long that vector is. So to find the unit vector, which I'll call it u, even though there's not like a specific notation for it, the vector u is going to be that vector v scaled by 1 over its own length. So I'm going to do 1 over the magnitude of v times the vector v, which is 1 over the square root of 38 times the vector 2, 3, negative 5. Do you see my notation there? 1 over the magnitude of v times the vector itself. And how do you do this? No, yeah, I'm going to do it inside right now. But I'm asking now, how do I do this? So I just each component gets multiplied. I don't want to say distribute because it's not technically distribution. Distribution is usually when you have like addition or subtraction inside and you're going through parentheses. But in essence, it's kind of like it, right? So I'm going to multiply through 2 over root 38, 3 over root 38, negative 5 over root 38. And then I'm going to have my conversation that I have with my students every semester. And I know some of you have had this conversation with, so if you already know my opinion on this, you don't have to repeat it. This is more for the people who have not had this discussion with me. Is that okay for me to leave that answer like that? Can I leave a square root in the denominator?
For you, yeah.
For me?
Yeah.
I'm okay with it? But I mean, mathematically, I have a couple of math majors in here, so is this okay or not? Because you're going to maybe one day be helping other people. If you're tutoring, are you going to tell them that's okay or not?
You can simplify it by one step, but it doesn't change the answer.
So it doesn't change the answer, but most people would rationalize that they'd multiply top and bottom by root 38, right? But does that absolutely have to happen? Are you going to tell other people you have to do it? Don't tell anyone. You're in the tutoring lab, right? Who else is the tutor? Anyone else tutor? Do not tell people they have to do it, all right? Because they don't. It's not necessary. It's the same answer, right? So why is it that we are taught incorrectly that you have to do it? Why? Because it looks nice. So I'm sorry, I have to do this, okay? If you've seen it before, sorry. Okay, so let's look at, I'm going off, that was our answer, by the way. 1 over the square root of 2, all right? Just separate yourself from the previous problem, this is brand new. I'm telling you this is okay to leave this as an answer, all right? Here's why other people are being told it's not okay and that you have to multiply the top and bottom by root 2. Are you all comfortable that if I multiply by root 2, top and bottom, I get this?
Yes.
Okay, so why is this okay and this isn't? Well, it comes from a history of when there weren't calculators. So imagine a day when there wasn't a calculator. There was maybe a slide rule or something like that. Before we had the technology, think about what this would require if I had to get some decimal approximation to it. Well, back in those days, people that were mathematicians, engineers, whatever, would have to know what the square root of 2 is. They would have to memorize it. They would have to memorize it as close or as many decimals as they could. So somewhere, whoever's working on this problem would know that this is the same as 1 divided by about 1.414. They might know it more decimals, I don't know. Depends on the person, right? But they would know that, right? Now imagine trying to do this now. Continue with this work. You don't have a calculator. So you go to old school division, wouldn't you? Inside the division box goes 1. Out here is 1.414, right? Like that. Now what you have to do is you have to try and figure out if you can think of a number that you multiply that by to get 1. Well, it's smaller than 1, isn't it? But what is it? So then maybe you start trying some numbers. It's going to take you a little while, right? This sucks. However, if you go and look at this, which is the exact same number as this, right? What would this require? Well, the top is 1.414. I've memorized that over 2, right? But now when I do the old school division, what goes in the box? 1.414, and out here goes 2. And isn't this easier? Because now what I'm saying is how many times does 2 go into 1? Well, it doesn't, so I put a decimal and a 0. Okay, how many times does 2 go into 14? 7. And do you see I can continue? Do you see how much easier that is to do by hand?
Yeah.
Yes? We want to rationalize because it aids us in the hand computation. That's an obsolete thing now, right? With the calculator. Now, most textbooks are going to want you to rationalize, but it's just this old thing we keep dragging along with us, okay? Now, I'm not saying it's not a good skill. Everyone here needs to know how to rationalize, especially like in Cal 1, when you get these expressions with variables in them, then you want to have the ability to do it. But when it comes to a number, this is fine. Just leave it like this. If we need a decimal, we're going to go to our calculator. It's going to be better than we could do by hand anyway, right? All right. We move on. Yeah, I wish I could do more history stuff in here, but
You always went off on tangents for history in Cal 2, like
yeah.
how the Chinese found pi. Their insane rectangles and circles method.
Law of exhaustion, or method of exhaustion. All right, standard basis vectors. So linear algebra, right? Linear algebra. Y'all are going to learn about something called an orthonormal basis.
I don't like it.
It sounds terrible, but it's basically means that, oh wait, hold on. I feel like I forgot something up here. I think I highlighted it in yellow, so I don't think I missed it. Yeah. Okay. Okay, let me talk about it first, then I'll go back to the orthonormal basis. All right, so there are two very important vectors, two really important vectors in R2. And they are called the standard basis vectors in R2. And they are the vectors 1, 0, and 0, 1. And we denote them with an I with a little caret symbol on top. It's called I hat. Do I have that on here? No. I hat, J hat, physics, that's the way they'll refer to it most likely. I hat, J hat. These are just vectors. And let's look at them visually. All right, let's look at what these vectors look like. Do you see the green vectors?
Yep.
That's I hat, that's the vector 1, 0. And J hat is the vector 0, 1, which goes straight up. They both have unit length, right? They both have a length of 1. And do you see that they are perpendicular to one another? The reason that's important is that if you give me any vector, see this vector u? Give me any vector, doesn't matter where I put it, I can always create this vector by taking some scalar multiple of this vector. Like in this case, I take this vector, multiply it by a negative number, and stretch it, negative 1.85 will give me that vector. And then I take this vector j, multiply it by 2.62 and make it that long. And do you see that if I do tip to tail, I get this vector? So you can get to any vector. In R2, you can get to any vector by taking some combination of adding this scaled, right? Scale this and add it to this scaled, and you can get to any vector you want. Or you can create any vector from those two. So like in linear algebra, have y'all gotten to that yet? No? No, you've taken the whole class, though, right? These are called, yeah, these are basis vectors, right? So they span the space. You can get to any vector from just these two vectors. But that's not what makes them super important, because these aren't the only basis vectors in R2. There are other basis vectors. What makes these super awesome is that they are orthogonal, they are perpendicular, and they are normal, which means they have unit length. So it's called an orthonormal basis. A basis, you can get to everything here with two vectors that are perpendicular and both have a length of 1.
We're in R2, right?
We're in R2, yes. Yes.
What's it mean for something to be orthogonal?
I'm getting to it.
Oh, okay.
Yep, it's coming up. All right, so that's in R2. In R3, we have 3 vectors. I hat, j hat, k hat, and they are right here. All right, so if y'all can see that, let's say that this is a vector with length 1. That is I hat. That is j hat. That is k hat. I hat, j hat, k hat. See them? So if I have any vector, I can create this vector by somehow taking multiples of I hat, multiples of j hat, multiples of k hat, adding them together, tip to tail, and I will get to this. So that's what this note right here says. Every vector in R3 can be written as a linear combination of those 3 vectors, I, j, and k. Now, you're not going to see much more of I, j, and k in here. Yes?
Why is it a hat instead of a E?
Yeah, I don't know why they use that notation. Yes?
I was about to ask, like, what's the point of that? It's like saying that anything can be multiplied by 1 to get whatever number, like the same number. Like,
What's the-
like the point of like having a pointer basis or like pointing it out? Like, I was gonna ask, like, what's the point of that?
Well,
That's what all confusion, yeah. The geometry of vectors, that's the only thing they can read, because you can basically make any vector, like you said, with a scalar value inside of your dimension. So that's one of the reasons why they use vectors. I mean, the even vectors.
yeah, the I hat, j hat, you're saying why
It feels like it's the same as like saying,
that 4 times 1 is 4?
yeah.
It is. It's exactly what it's saying. 4 times 1 is 4, right? But the difference is that 1 there is the additive identity, right? I mean, sorry, multiplicative identity. So the number 1, remember we were just talking about 0? 0 is called the additive identity. You add 0 to anything, you get itself. Well, in every field, you must have a multiplicative identity as well. You have to have something that you multiply, and it leaves it unchanged. The number 1, in R1, the number 1 would be your multiplicative identity. The question is, in higher dimensions, what does it look like, right? So it would be a vector. It would be the vector 1, 1, 1. But that vector is made up of other vectors, I, j, and k. So it's just that they're the cleanest vectors that you can use to move around the space. You don't have to use a vector here, here, and here. They don't have to be orthogonal, and they don't have to be unit length. I mean, imagine I gave you a vector that was 3 units long, and I called that I hat. And then I gave you one that's 2 units long, called that j hat, and then one that's 5 units long, called that k hat. Let's just say I did that, right? Could you get to every vector in that space with those 3?
Yeah.
Do you agree that we could? Even if they didn't have length of 1, could I get around? I should be able to? Okay, so that's another basis for the 3-dimensional space. What we're looking for is like the best basis, where those vectors are maybe all perpendicular to one another, and maybe they all have length 1, because they're super clean vectors, right? Look at the vectors, 1, 0, 0. Isn't that a nice clean vector? Isn't this a nice clean vector? So we're looking for this really, really nice way to get around, and that's it, I, j, and k. Does that help a little bit?
Yeah.
Okay. I'll say one more thing. I don't want to go too far off on this. If you agree that you can get around 3-dimensional space with I, j, and k, what if I gave you these vectors? Those 3 vectors, okay? None of them, they're not orthogonal to one another. Do you see that? Mm-hmm. Can you get around 3-dimensional space with those 3? What do you think? Think so? Can I get to a vector right here? How? How could I do it? I'd multiply this one by a negative, right, which would bring back here. And then I would multiply this one by some number, bring me up. And if I need to move in any other direction, I could use this one. So as long as these three vectors are not parallel, okay? As long as these three vectors are not parallel, they will span three-dimensional space. I'm using words that we haven't even defined, but it's an idea. Do you understand the idea? So this would also be a basis for R3. And then I could have just like made this one go this way. Now that's another basis, right? So IJK is the standard basis. It's the best. It's the orthonormal. They're orthogonal, and they all have a length of 1. It's like the cleanest basis. Okay, I'm done. All right, we've got to keep going, yes? So this is an opportunity for us to just use some notation, all right, just to make sure we understand the notation, the language. I've got you a vector there, 2, 3, -5. I want us to write it as a linear combination of the standard basis vectors. So here's how I'm going to do it. Watch me do it for the first time, then hopefully you'll catch on. It's not crazy, all right? So I'm going to start here. There's my vector v. First thing I'm going to do is I'm going to act like that's three vectors being added together. So it's the vector 2, 0, 0, plus the vector 0, 3, 0, plus the vector 0, 0, -5. Knowing what you know about vector addition, do y'all see that you can kind of deconstruct that thing out or kind of rip it apart into those three vectors being added together? Y'all agree with that? Yeah? Then on this first one, you see the 2? If I imagine pulling the scalar out of that vector, you would be left with the vector 2 times the vector 1, 0, 0. And if I just multiply this, scale it, I would get that, wouldn't I? I can do the same thing here, can't I? So I would pull what out of this one? 3, and then what vector would go here? 0, 1, 0. And then finally, what should I pull out of this one? -5. And I get the vector 0, 0, 1. And hopefully we recognize these three very important vectors, right? This is I, this is j, this is k.
So we write it then as 2i, 3j.
2i hat plus 3j hat minus 5k hat. So when you're in a physics class and you see 2i plus 3j minus 5k, that's just another way of saying the vector 2, 3, -5. Or if you're in a linear algebra class, that's just another way of writing the vector 2, 3, -5 if you do a vertical vector. We have all these notations. It'd be nice if we just all use the same notation. Wouldn't that be great?